I would like to invite the author, Chen Li, to make the presentation called the Gossen first law in the modeling for demand-side management, a first heat pump case study. So, Cheng, the floor is yours.
Good morning to all attendees. My name is Chang, and I'm from Karlsruhe Institute of Technology. The topic of my presentation today is Gossen's first law in the modeling for demand-side management with a heat pump case study. My presentation will include at least 5 parts. First, I will briefly describe the core idea of my work as an abstract. Then, second, the motivation and the problem statement of our work. Then I will explain the methods and the models we have proposed in the paper. And in the first part, I will show the results together with the analysis. And also some conclusions we have got. So let's start with the core idea first. This core idea is mainly inspired by the Gossen's first law in economics, which is also known as the law of diminishing marginal utility. And it describes like a decrease in marginal utility with an increased consumption of a good or service. And this is observed in many areas. A famous example is like you are hungry and you want to eat a pizza. And the first slice pizza will normally give you more pleasure than the second slice. So that's a decrease in marginal utility. And we thought maybe that we could find this kind of similar pattern in our research field. And more precisely is the relationship. How can we reach an optimum between the utility and the complexity in the demand-side management? Now let's move to the second part. I will explain the specific motivation and the problem statement. So when we talk about like demand-side management, the first that comes to mind is in the industrial sector, since it has the most potential and the associated equipment. However, due to the energy transition, a model building will contain more and more electricity related components, as we see in these 3 days. So for example, like a heat pump, a solar system, a charging station for EVs, or even like a fuel cell system for as a home power plant. And I've seen many modeling-based works. Energy systems can generally categorized into these 3 types: black box, gray box, and white box. And each type has its own advantages, but also limitations. For instance, black boxes are mainly data-driven, and they don't rely on the physical details of a system. However, massive, highly resolved data sets, such as node files, are necessary for good training. And the lack of physical details can raise concerns on its reliability and interpretability in practice. And in contrast, white boxes are based on detailed physical structures of a system. However, it requires a lot of expertise for specific energy system, and this could lead to enormous effort for modeling, and the expressibility of the models could also be limited. And as mentioned in the abstract, so for the modeling, so the key question is what kind of this relationship is satisfied between the complexity and the utility in the modeling, so that we could with this question we could like find the optimum or balance for our purpose. And as mentioned in the abstract, under the inspiration of this Gossen's first law, we have proposed the hypothesis that in general the complexity and utility relationship could be represented by a diminishing marginal utility curve in the context of DSM application. And in the first case study, we will focus on the heat pump here. Okay, let's move to the part of methods. As with Gossen's first law, the marginal utility itself is an abstract concept, and it needs to be quantified first. Similarly, the quantification for complexity and the utility are also crucial for virtualizing the relationship between them. And for the quantification of complexity based on different purposes, there are several options to choose. For example, time scales. We could use like large time scales to simplify a whole process. When this transient process with this system non-decisive it. So in this in this way, we could like simplify the whole modeling process. However, this option has a limitation, is that it's not possible to differentiate the complexity of the same model. And another option would be power range, because different power ranges would have a significant impact on the dynamic responses of a system and corresponding controls. But the limitation is also significant in this case, because it is not because the power range for a given energy system is normally determined. So it's not always possible to be artificially changed just for the simulation or for the research. And a third way of quantification of complexity is the number of required parameters, because on a structural basis, any model is like a compilation of different input-output parameters. And because of this option gives like the best applicability and feasibility among the three options here. So based on this option, namely the number of required parameters has been chosen to for the quantification of complexity in our work. And for the quantification of utility, we should be aware that the main goal of the DSM is to improve the flexibility of a power system. So the typical ways for quantifying of flexibility, namely load shifting, peak shaving, reduction of energy use, and value fitting can also be used for the quantification of utility here. And in addition, it is worth noting that a model must be verified in the first stage before it is used to analyze the flexibility. So the accuracy of a model is also another possibility for the quantification of utility. And for that, we can quantitatively use some common but useful statistic matrix in this descriptive mathematics. For example, root mean square error, max error, and MIP. And in our current work, we focus on the first stage. We analyze the accuracy of different models in an offline simulation. And in order to reduce the impact of absolute values on the accuracy analysis, we have chosen the MIP and its variant as the matrix for our analysis. We will see more on the next slides. Okay, let's come to the modeling. The picture on the left shows the schematic heat matrix, and the electrical circuit of our experimental house. And in our work, we focus on the heat pump system here, and it consists of three main components. The first is these U tubes as the ground heat exchanger, and the ground source heat pump itself, and a hot water tank as the hot pump storage. And the modeling is based on these three main components. For the ground heat exchanger, we have used the change in inlet and outlet temperature together with the specific heat capacity and the mass flow of the brine to calculate the absorbed thermal power at each time step. And this is also like the difference between the thermal power at the end and the consumed electric power. And for the heat pump, we use the coefficient of performance, or COP for short, to characterize the overall performance of the heat pump. And in actual operations, this COP, this coefficient is influenced by many factors, such as supply temperature, return temperature, or outdoor temperature. And in our work, we have employed second-order polynomial regression to directly calculate the COP based on in consideration of the outdoor temperature with the declared data from the heat pump manufacturer. And another possibility is we can also directly measure the thermal power and the consumed electric power over a period of time, and we obtain an average value from it. As the central storage for thermal energy, the temperature change and the corresponding energy changes in the storage have a significant impact on the overall system. Assuming the density and the specific heat capacity of hot water is constant, we can use this simple formula to calculate the energy change in the storage. Okay, let's come to the first part for results. As mentioned before, we have used the number of required parameters as the way for quantifying complexity. And by combining the mathematical models on the last slide, we have introduced the 4 different model classes A, B, C, D, with a decreasing complexity in terms of required number of required parameters. And the table on the right presents the applied parameter to each model class. And for the simulation and analysis, we have selected a typical winter day in February this year, and measure the data 24 hours continuously. And the diagram here shows the results together with the measurement. And we can see that the results from the model A is almost like identical to the measurement, whereas models B and C show some large deviations at some points in time, such as hour 10 or hour 15. And this could be because in these 2 models, we have not considered the energy change in the storage. So maybe that's the reason for this big deviation in some time point. And the simplest model D shows much larger deviation than other models. And the table here, we have shown the overall statistic features of these these 4 models with the help of MapMe and the MapMax. And this data also are consistent with our analysis. So the most complex and accurate model has the smallest error. And in order to calculate the exact utility of our model, we have defined a formula here, U, for the calculation of utility. U represents utility here. And with this definition, we illustrate the relationship between utility and complexity and the utility in this diagram. And it demonstrates that the results are basically in line with our hypothesis at the beginning. However, due to the limitations of data points, this blue line is not as smooth as an ideal diminishing marginal utility curve, which is presented here in orange dashed line. Okay, now let's summarize some key points of the work and give a hint for the future work. So in the current work, we have proposed a hypothesis for applying to apply the Gossen's first law for describing the relationship between complexity and the utility in the context of DSM applications. And in our first case study, we have developed 4 different model classes with different quantified complexities to investigate this diminishing marginal utility. And we have then defined a new quantitative indicator to calculate this utility in the first stage. And the first results appear consistent with our hypothesis. And in the second stage, we have to integrate these different models into a control system to investigate the impact of different models on the flexibility. And that's a hint of our future work. So that's all for my presentation. If you have any questions, please feel free to ask. Here's my contact information too. Thank you.
Thank you for the presentation, Chang. Now we are open for questions. Anyone has questions? First of all.
Thank you. Thank you for a very nice presentation. I have a question for your slide number 12. This one, yes.
Yeah.
Now, you said you have chosen a typical day in February.
Yes.
Right?
Yes.
And to show the accuracy of your 4 models. My experience is just that, you know, these when you pick a day from training different models, and you have all the days throughout the year. There can be quite some variation in the accuracy of the models.
Yeah.
I mean, some models just performs better in summer than in winter, or there's just something. So now you pick this day. So I think I have two questions.
Okay.
Why you pick this day in particular, and how your models perform throughout the year.
Okay. The first question, we just make an agreement with our colleagues in the lab. So they have chosen this day. So I don't know the data before I know the arrangement. And for the second question, you have it's more convincing when people like use more data for like a whole year, for example. So that's actually a week list, I should say, for this simulation, because we have only like selected one day. So maybe it's not so convincing when people have like only 1 day data. So yeah.
Anyone else has questions? Okay.
Hi.
So maybe I just didn't understand, but how did you select the various functions that you used in the various complexities for the models? Because I don't know, it seemed a bit.
Yeah.
I think this is a slide you show with all the crosses for the different models, but
Yeah.
like, how did you select that?
Select the
Try to go a bit further in the slide.
further.
One more.
One more.
This one, like
Here.
you put these different x's. Why do you put them in these specific places?
Because it shows the specific parameters that we have. Because on the left, I just showed the number, like 11 or 6, and on the right, I show which 11 parameters are chosen.
Yes, but so when you then start reducing the number of parameters, why do you choose those specific 8 and not like how do you choose that?
Because that's a common way, like for reducing models or for reducing complexity. So like for example, if you some parameters are hard to measure, and you will treat it like a constant when it is not so important. You can either like ignore it or treat it as a constant. So it's like a common way. So for example, if I think the temperature change in the storage are so difficult to measure, and I will choose to ignore it and treat it as a constant. So I won't consider the energy loss in the storage, and that's why reason for the deviations here for model B and C, because I didn't consider the energy loss in the storage. Yeah.
Okay, thank you.
You're welcome.